Hi everyone, my name is Dr. Naga Malleswari, Assistant Professor, Department of Mathematics from VNR JYOTHI Institute of Engineering and Technology, Hyderabad. In today's lecture, we discuss about the topic residues. So in that, we have to evaluate the residues by formula and by residue theorem. Let us begin with the definition of residues. The coefficient of 1 by z minus a in Lorentz series expansion of f of z. So in last lecture, we already discussed what is Lorentz series expansion. Lorentz series expansion f of z is equal to summation n is equal to 0 to infinity an z minus z naught whole power n plus summation n is equal to 1 to infinity bn by z minus z naught whole power n. Here summation an z minus z naught whole power n is analytic part and summation n is equal to 1 to infinity bn by z minus z naught power n is principal part, where an is equal to 1 by 2 pi I integral over c1 f of z into dz by z minus z naught power n plus 1 and bn is equal to 1 by 2 pi I integral over c2 f of z into dz by z minus z naught whole power minus n plus 1. Here the coefficient of 1 by z minus a in Lorentz series expansion of f of z about the isolated singularity z is equal to a. So this is called residue of the function f of z at the point z is equal to z naught or at the point z is equal to a. Next definition is residue at the pole. If f has a pole at the point z naught, then residue of the function f of z at the point z is equal to z naught is given by limit z tends to z naught, z minus z naught into f of z is equal to 1 by 2 pi I integral over c f of z into dz. So this is the formula for residue at the pole. This is another alternate method to find out the residue at a pole. And in previous definition, we have to find out the residue by using Lorentz series expansion. And in this alternate method, we have to find out the residue at a pole. Next, Cauchy residue theorem. F of z is analytic function. C is the closed curve. Z1, Z2, Z3 up to and so on Zn are finite number of poles within the closed curve C. R1, R2, R3 up to and so on Rn be the residues of the function f of z. Then these poles we have to find out the residue of the analytic function f of z. And it is given by integral over c f of z dz is equal to 2 pi I into sum of residues. So sum of residues means here we are taking R1 plus R2 plus R3 up to and so on Rn. So we can write like this also, 2 pi I into sum of residues. Next definition, residue at a pole of order m. F of z is analytic function. C is the curve and it has a pole of order m at the point z is equal to z naught. Then the residue at z is equal to z naught is given by residue of f of z at z is equal to z naught is equal to limit z tends to z naught 1 by m minus 1 factorial d power m minus 1 by dz power m minus 1 z minus z naught whole power m into f of z. So this is the formula for residue at a pole of order m. So previously we discussed residue at a simple pole. And now this is the formula for residue at a pole of order m. Next, at the point z is equal to z naught, be the singularity of a function f of z if there is no other singular points are existing within the small circle surrounding the point z is equal to z naught. So thus this point is said to be the isolated singularity point. Otherwise we call it as a, or we termed it as a non-isolated singular point. Here function is given f of z is equal to z plus 1 by z minus 1 into z minus 2. Given function f of z is analytic function. It is differentiable function everywhere, but except at the points z is equal to 1 and z is equal to 2, it is not differentiable, or it is not an analytic function. Also, there are no other singularities are existing for the function f of z. So, z is equal to 1 and z is equal to 2, we call it as a isolated singularities for the function f of z. Next definition, residue at infinity. If f of z is the function, f of z has an isolated singularity at z is equal to infinity, or is an analytic function, then residue at z is equal to infinity is defined as residue of the function f of z at z is equal to infinity is equal to minus 1 by 2 pi I integral over c f of z into dz. See the example problem for clear understanding. Find zeros and poles of z plus 1 by z square plus 1 whole square. We have to find zeros and poles of the function f of z. First we have to note down the given function. F of z is equal to z plus 1 by z square plus 1 whole square, that equal to z plus 1 whole square by z square plus 1 whole square. First we have to find out zeros for the function f of z. Zeros. To find the zeros of the given function f of z is given by f of z is equal to 0. So to find out the zeros of the given function f of z, and it is given by f of z is equal to 0. So f of z is equal to 0 means what is f of z? F of z is z plus 1 whole square by z square plus 1 whole square equal to 0. That equal to z plus 1 whole square is equal to 0. Therefore, z is equal to minus 1 comma minus 1. Therefore, the zeros of the function is minus 1 comma minus 1. Z is equal to minus 1 comma minus 1 is 0 of order 2. Next, we have to find out poles. So, how we can find out the poles? By equating denominator to 0. Function f of z is z plus 1 whole square by z square plus 1 whole square. Equating denominator to 0. Equating denominator to 0. We get z square plus 1 whole square is equal to 0. Z square plus 1 whole square means it can be written as z square plus 1 into z square plus 1, which is equal to 0. Z is equal to plus or minus I. We get I, comma I, minus I, minus I. Therefore, Z is equal to I and Z is equal to minus I are both having the poles of order 2. Poles of order 2. So, zeros, Z is equal to minus 1 and minus 1. 0 of order 2 here we get, and poles Z is equal to I and minus I. Both are having the poles of order 2. Next, we have to evaluate the residues by using Lorentz series expansion. Find the poles and residues of 1 by z square minus 1. We have to find out the poles and residues for the given function f of z. Let f of z is equal to 1 by z square minus 1. And it can be written as 1 by z minus 1, z plus 1. First, we have to resolve it into partial fractions. Resolve it into partial fractions. 1 by z minus 1, z plus 1 is equal to a by z minus 1 plus b by z plus 1. 1 by z minus 1, z plus 1 is equal to, first take LCM here, z minus 1, z plus 1. A into z plus 1 plus b into z minus 1. Cancel the denominator. We get 1 is equal to a into z plus 1 plus b into z minus 1. First, put z is equal to minus 1. We get, so we have to find out the values of a and b. So for this, first we are taking z is equal to minus 1. 1 is equal to a into minus 1 plus 1. Here we get 0. Plus b into minus 1 minus 1 minus 2. B is equal to minus 1 by 2. We get the value of B. Next, to find out the value of A. For this, we have to take z is equal to plus 1. Then substitute the value of z is equal to 1. 1 is equal to a into 1 plus 1, we get 2, plus b into minus 1 plus 1, 0. A is equal to 1 by 2. So here we get the values of a and b. A is 1 by 2 and b is minus 1 by 2. Substitute a and b values in this equation. We get f of z is equal to, a is 1 by 2 and b is 1 by 2. 1 by 2 of 1 by z minus 1 plus, sorry, here we get minus 1 by z plus 1. Next what we have to find out here? We have to find poles of the function f of z. The poles of the function f of z are equating denominator to 0. We get 2 poles here and 2 are the simple poles. One is z is equal to 1 and another one is z is equal to minus 1. Z is equal to 1 and z is equal to minus 1. Both are the simple poles. Next we have to find out the residue. Find the poles and residue. So first part is completed here. We have to find out the poles. We get pole of order 1. Next we have to find out the residues. Residues by using Lorentz series expansion. We expand the function f of z in Lorentz series in powers. So first what we have to take at the point z is equal to, at the point z is equal to 1. So we have to expand the powers of f of z in Lorentz series in powers of z minus 1. First we have to note down the function here for this expansion. F of z is equal to 1 by 2 into 1 by z minus 1 minus 1 by z plus 1 equal to 1 by 2 into 1 by z minus 1 minus 1 by z plus 1 is there. But we have to expand this in powers of z minus 1. We get z minus 1 plus 2, that equal to 1 by 2 into 1 by z minus 1 minus 1 by z minus 1 plus 2, which is equal to 1 by 2 into z minus 1 minus 1 by 2 into 1 by z minus 1 plus 2. Put z minus 1 is equal to some u. Here we are taking the assumption z minus 1 is equal to some u. That is equal to 1 by 2u minus 1 by 2 into 1 by u plus 2 equal to 1 by 2u minus 1 by 2 into 1 by, here in denominator we are taking 2 common. We get 2 into 1 plus u by 2 is equal to 1 by 2u minus 1 by 2, and here 2 is there. We get 1 by 2 into 1 plus u by 2 whole power minus 1. That equal to 1 by 2u minus 1 by 4 into 1 plus u by 2 whole power minus 1. That equal to 1 by 2u minus 1 by 4 into, expand this one, 1 plus u by 2 whole power minus 1. Expansion is 1 minus u by 2 plus u by 2 whole square minus u by 2 whole cube plus and so on. So this is similar to the expansion of 1 plus x whole power minus 1. 1 plus x whole power minus 1 expansion is 1 minus x plus x square minus x cube and so on. But in place of x here u by 2 is there, so that we are taking 1 minus u by 2 plus u by 2 whole square minus u by 2 whole cube and so on equal to 1 by 2 into, what is u here? Z minus 1 minus 1 by 4 into 1 minus z minus 1 by 2 plus z minus 1 by 2 whole square minus and so on. Here the coefficient of 1 by z minus 1 is 1 by 2. Therefore, the residue at z is equal to 1 is 1 by 2. So, we get the residue at the point z is equal to 1 is 1 by 2. Next, we have to find out the residue at the point z is equal to minus 1. Residue at the point z is equal to minus 1. We can expand the function f of z in Lorentz series expansion in powers of z plus 1 here. We expand the function f of z in Lorentz series in powers of z plus 1. Function f of z is 1 by 2 into 1 by z minus 1 minus 1 by z plus 1. But now we have to expand it in powers of z plus 1 so that we can write the denominators as 1 by, here z minus 1 is there. We have to mention this in terms of z plus 1. Z plus 1 minus 2 minus 1 by z plus 1. Here there is no change because it is already there in powers of z plus 1. 1 by 2 into 1 by z plus 1 minus 2 minus 1 by z plus 1. That equal to 1 by 2 into, assume this, put z plus 1 is equal to some u. We get 1 by u minus 2 minus 1 by u. We get 1 by 2 into 1 by u minus 2 minus 1 by u. That equal to 1 by 2 into, take here minus 2 common, minus 2 of 1 minus u by 2 minus 1 by u equal to 1 by 2 into minus 1 by 2, 1 minus u by 2 whole inverse minus 1 by 2u. That equal to minus 1 by 4 into 1 minus u by 2 whole inverse minus 1 by 2u. That equal to minus 1 by 4 of, expand this one by using the formula 1 minus x whole power minus 1. 1 plus u by 2 plus u by 2 whole square, u by 2 whole cube and so on, minus 1 by 2u equal to minus 1 by 4 into 1 plus, we are assuming z plus 1 is equal to some u. So, in place of u, we are taking z plus 1 by 2 plus z plus 1 by 2 whole square, z plus 1 by 2 whole cube and so on, minus 1 by 2 into z plus 1. See here, the coefficient of 1 by z plus 1 is minus 1 by 2. The coefficient of 1 by z plus 1 is minus 1 by 2. Therefore, the residue at z is equal to minus 1 is minus 1 by 2. This is the problem which is related to poles and residues. This is alternate method to find out the residues. See the example. Find the residues of z e power z by z minus 1 whole cube at its pole. we have to find out the residue for the given function f of z. So first we have to note down, let f of z is equal to z e power z by z minus 1 whole cube. First we have to find out poles for the given function before finding the residue. So how we can find out the poles? By equating denominator to 0. Equating denominator to 0. We get z minus 1 whole cube is equal to 0. Z is equal to 1, 1, 1. Therefore, z is equal to 1 is pole of order 3. Next, we have to find out residue for the given function f of z. Residue at the point z is equal to 1. But here we get z is equal to 1 is pole of order 3. We have to find out the residue of the function f of z of pole of order m is given by residue of f of z at z is equal to z naught is equal to 1 by m minus 1 factorial limit z tends to z naught d power m minus 1 by dz power m minus 1 z minus z naught whole power m into f of z. Here m is equal to 3 because we get z is equal to 1 is pole of order 3. So that here we are taking m is equal to 3 and a is equal to 1. Residue of the function f of z at z is equal to 1 equal to 1 by 3 minus 1 factorial limit z tends to 1 d power 3 minus 1 we get d square dz square z minus z naught whole cube into f of z, that equal to 1 by 2 factorial limit z tends to 1 d square by dz square into z minus z naught whole cube into what is the given function f of z? F of z is z e power z by z minus 1 whole cube. Here z naught is 1. 1 by 2 factorial limit z tends to 1 d square by dz square into z minus 1 at the point we are taking. What is the point that we get? Z is equal to 1 whole cube into z e power z by z minus 1 whole cube. Z minus 1 whole cube, z minus 1 whole cube cancel. Then we get 1 by 2 factorial limit z tends to 1 d square by dz square into z e power z, that equal to 1 by 2 factorial limit z tends to 1 d by dz of Differentiate it with respect to z. We get z e power z plus e power z. We are applying uv rule. uv dash plus v u dash. That equal to 1 by 2 factorial limit z tends to 1. Again differentiate it with respect to z. We get z e power z plus e power z plus e power z equal to 1 by 2 factorial. Apply the limit z tends to 1. We get, in place of z here we are taking 1. 1 into e power 1 plus e power 1 plus e power 1. That equal to 1 by 2 factorial 3e is equal to 3e by 2. Next, see another example. Find the poles of the function f of z is equal to 1 by z plus 1, z plus 3 and residue of these poles. Let f of z is equal to 1 by z plus 1, z plus 3. First we have to find out the poles for the given function f of z. We can find out the poles by equating denominator to 0. Then we get z is equal to minus 1 and z is equal to minus 3 are the poles. Z is equal to minus 1 and z is equal to minus 3 are the simple poles here. Next, we have to find out the residue at z is equal to minus 1. Residue of the function f of z at z is equal to, point is minus 1, is given by residue of f of z, z is equal to minus 1, which is equal to limit z tends to z naught. So here point is minus 1. We can take the point here, z tends to minus 1, z minus z naught. So what is the point z naught here? Minus 1. Minus of minus 1 we get plus 1 into f of z. f of z is 1 by z plus 1, z plus 3. Z plus 1 cancel. We get limit z tends to minus 1, 1 by z plus 3. Apply the limit here. Then we get 1 by minus 1 plus 3. 1 by 2. Therefore, the residue of the function f of z at the point z is equal to minus 1 is 1 by 2. Next, we have to find out residue at z is equal to minus 3. Residue of f of z at z is equal to minus 3 is limit z tends to minus 3, z plus 3 into f of z. What is f of z? 1 by z plus 1 into z plus 3. Z plus 3 cancel. That equal to limit z tends to minus 3 into 1 by z plus 1. Apply the limit. We get 1 by minus 3 plus 1. Minus 1 by 2. Therefore, the residue at z is equal to residue at z is equal to minus 3 is minus 1 by 2. Next, see the problems related to evaluation of integrals by using residue theorem. Evaluate closed integral over C 4 minus 3z by z into z minus 1, z minus 2 into dz, where C is the circle, mod z is equal to 3 by 2 using residue theorem. Residue theorem is f of z is equal to 2 pi I into sum of residues. Here we have to find out the residues. Let f of z is equal to 4 minus 3z by z into z minus 1, z minus 2. First, to find out the poles for the given function f of z. So, to find out the poles, we have to equate the denominator to 0. We get z is equal to 0, 1 and 2. Here C is the circle, mod z is equal to 3 by 2 is given. Mod z is equal to 3 by 2. First draw a circle, x-axis, and here it is y-axis, 0, 1, 2, 3. Mod z is equal to 3 by 2 means circle with center 0 and radius is 1.5. So, approximately here we get radius. But the poles that we get here are z is equal to 0, 1 and 2. Z is equal to 0 and 1 are the poles lie inside the circle. So clearly we get two poles here, z is equal to 0 and z is equal to 1. These two are lie inside the circle. So here we are taking, it is enough to take z is equal to 0 and z is equal to 1. Next, we have to find out the residue. Residue at z is equal to 0. Residue of the function f of z at z is equal to 0 is given by limit z tends to 0, z minus 0 into f of z. What is f of z? 4 minus 3z by z into z minus 1, z minus 2. Here z is there and here also z is there. Cancel these two. We get limit z tends to 0, 4 minus 3z by z minus 1, z minus 2. That equal to, apply the limit, we get 4 by minus 1 minus 2. That is equal to 2. Residue at the point z is equal to 0 is 2. Next, we have to find out the residue at the point z is equal to 1. Residue of f of z at z is equal to 1 equal to limit z tends to 1, z minus 1 into f of z. F of z is 4 minus 3z by z into z minus 1, z minus 2. Here in denominator z minus 1 is there and here z minus 1 is there. Cancel these two. We get limit z tends to 1, 4 minus 3z by z into z minus 2. Next, apply the limit here. We get 4 minus 3 by, in place of z here we are taking 1. 1 minus 1. That is equal to minus 1. Residue of the function f of z at z is equal to 1 is minus 1. Next, apply residue theorem here. By residue theorem, f of z is equal to 2 pi I into sum of residues is equal to 2 pi I into R1 plus R2. Here we get two residues. 2 pi I into R1 is first residue is 2 and second residue is 1. 2 pi I into 1, that is equal to 2 pi I. Try the following problems. Determine pole of the function cot z. Second one, evaluate integral dz by z square plus 4 whole square where c is mod z minus I is equal to 2. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.